Recording. Hi, this is Hamad Kanakia, and as a part of a Vishwakarma Prize competition that is being held this year by Makerbone Foundation, which is centered on the topic of water and sanitation. The purpose of this Vishwakarma Prize is to actually get the engineering students who are inventive to be rewarded and encouraged to do work on some real or practical problems. Here I am today talking with Professor Jaichander from IIT Gandhinagar. And without further ado, I will ask him himself to introduce himself and talk a bit about his history of the CV.
Thank you, Hemant. I'm glad to be here and to be associated with this prize competition. So my name is Jaichander. I'm an assistant professor in mechanical engineering at IIT Gandhinagar. I'm also affiliated with the Center for Sustainable Development here. So I'm also the current occupant of the Kanchan and Harilal Doshi Chair for Water and Sanitation. Prior to joining IIT Gandhinagar, I completed my PhD from MIT. And before that, I did my bachelor's also in mechanical engineering from IIT Madras. So that's my brief history.
Wonderful. I think to begin with, I myself am actually quite interested in understanding what got you attracted to doing the research in this area. I myself come from computer science, so I find it hard to understand people who work in real world problems. So please, how did you get into it?
Sure. So I got into working on water as a part of my master's and PhD work at MIT. So as mechanical engineers, we often think about energy. So actually, my work is at the intersection of energy and water, and not specifically in water itself. So we've always thought about energy in the context of improving energy efficiency of various energy conversion systems like power plants, automobiles, flights, things like this. So that framework is something that we study. It's now a part of the, it's like a well-established concept in mechanical engineering. And even at an undergraduate level, we study that in quite a bit of detail. So the PhD group that I joined with Professor John Leonhard, they were taking this framework and applying it to water treatment and particularly desalination, where you can think of it as a process to convert, high-grade energy into good quality water. And so the question there again becomes, how can you do this efficiently? So that's broadly the context. So we use the tools of thermodynamics, heat and mass transfer, but we're applying it in the context of water treatment and desalination.
Wonderful.
So maybe just a small addition to this. So particularly our focus is on desalination because that is probably the most energy intensive among the water treatment processes. As you can imagine, separating pure water from a solution that has like other dissolved impurities in it is going to be energy intensive by the nature of the process itself.
So are you actually taking a seawater or a saline water and making it into a potable water kind of a target, or is it a sewage or a dirty water, as they say, and make that into an industry quality pure water? Where is the, tell us a little bit about your research and what is the state of the art? Where are you finding interesting problems? Things like
sure.
that.
So this field of desalination is actually all encompassing in terms of the different projects that you mentioned, problems that you mentioned. But when we say desalination, we usually focus on the seawater because that is like the largest, reservoir of salt water that's available. A lot of people have access to it. And converting it into potable drinking water is an important, is like a major task when it comes to desalination. When we think about potable water itself, the source can also be not seawater, it can be groundwater. So in the context of India, if you are inland, even then it's quite possible that if you dig in and if you are like tapping into groundwater sources, you do not get like potable quality water as such. You might get water that is relatively salty, what we call brackish water, And in those cases also, the same technologies are useful. The technology that I was working on for a lot of time was something called membrane distillation. So that is kind of like an up and coming technology. It's not the leading technology in this field. And the relative advantage of this technology is that it can handle really salty water streams. So therefore, the applications that are usually targeted with this technology are more in the brine management space. So let's say you have seawater desalination and you produce a salty brine. What do you do with it? Can you extract more pure water from this, either in the context of seawater desalination or in the context of industrial brines, where there are regulations towards preventing industries from discharging their brines. So it makes sense for them to try to extract as much pure water from this brines for recycling purposes, and eventually even get to like a zero liquid discharge state. So actually, my research has been focused on this one technology, but I've also worked on other technologies like reverse osmosis, various innovations in reverse osmosis itself, then electrodialysis. So actually, I've worked on a range of technologies, each often with its own niche application where it makes a lot more sense.
And so it seems one of the focus of your research is the reduction of the energy input needed to do desalination. Is there any chemicals involved in the work you do as well?
So usually, if the process is powered by electricity, like in the context of pressure-driven reverse osmosis or in electrodialysis process, our focus is to look at this from a system level and think about where the losses are happening and how to optimize the system, which component of the system, if you improve, can you actually get maximum impact in terms of energy efficiency. So here per se, there are no chemicals involved. However, chemicals become important when we again kind of zoom out a little bit more. So one of the recent work that we are publishing is related to energy management in industry. So in the context of industry, the chemicals that they use in the industrial process is what affects the the composition of the wastewater itself. And this has a significant impact on the energy for water treatment. So it sometimes it isn't really considered in that perspective, but it is possible in the context of like green chemistry or green management to improve energy by choosing chemicals wisely. Chemicals also come into the picture in terms of pre-treatment, but this is not something that I focus a lot on.
So the kind of research you do when it is organized into a system level stuff, is that something that is done at a very large scale? You do it for a town or a village or a small campus? What is the likely use of what the applied work of your research?
Right. So the applied research that we focus on is at the system level, by which we mean the desalination system. And often these desalination systems are modular. So at least the RO process, electrodialysis process, these are built using membranes. And so the scaling up of this process is relatively straightforward, in the sense that that's the reason that you see these systems being applied all the way down to like a household level, as well as being applied, at the large city level also. Of course, the technologies that are used, the economics drives whether you use specific energy recovery devices or not. But the fundamental process is more or less the same. So if you work on it at one scale, it kind of translates to across these different scales.
And so, if I understand you well, what you are saying is that scaling is a little bit easier because it's a very modularly built desalination plant.
Exactly. Yeah.
And clearly the work you are doing is quite relevant to society in general, and particularly if it's a seawater areas in say near desert like places like Rajasthan or others which are near the seawater coastal areas would benefit quite a lot if they are able to do such a thing. And also, if you can have a village level systems, it would basically avoid having to lay down a lot of pipes to carry the water around or dig a canal to do the work. Anyway, so I would like to focus a little bit about, and this is directed towards the engineering students who may be interested in this area, as to what do you see as their progression if they worked on things like this in undergraduate work or even a postgraduate work, how likely they are to find a job in industry or work in the research like you did. Is it a popular area?
I think it's a very popular area right now, especially with sustainability being at the forefront of a lot of our discussions. So a lot of industries have their offices focused on these topics. They are no longer happy with just outsourcing their water treatment requirements. They want to optimize these to the extent possible, make sure that they are using resources the best possible, because they also have a clear impact. It also has a clear impact on their bottom line. Often, when you start doing water treatment towards zero liquid discharge, it can become a significant portion of your overall operating expenditure. So I see this becoming important in a lot of industrial settings. So somebody with experience in these topics would be of value to these industries. Besides this, there are of course niche applications in various R&D areas, like if you think about defense, if you think about any other industry. Again, water and energy, I think, are relevant subjects for a lot of these industries, I would say.
So, because this competition is all about making things, I wonder how much of making things or building prototypes to demonstrate the concept or maybe proof of concept kind of systems would be important in the kind of work that you have done or are doing.
Right. So in a lot of my research, it has involved lab scale setups to study the performance of these systems. Often we can come up with numerical or analytical models, but they can only predict up to first order, and the predictive power is also contingent on various parameters that are like going to describe the real membranes. So in order to understand how a real membrane works, it's usually, I mean, it's more like you do the building and measurement, and then you try to fit a model to this. That's the way it works. And also the cutting edge of this field is usually based on the kind of experiments or the setups that you mentioned, like prototypes setups, which show promise, and then people try to figure out why it works. Often somebody just reports that something works well, and then people try to figure out why or how it works later.
So I'm curious about when you publish your research into an academic setting or a journals, is this an area in which you require experimental results to be presented along with the theoretical models, or
yes,
just theoretical models work well enough?
So I think it depends on the kind of system that you're working with. So if you're working with a well-established system where there are thousands of experiments out there already, then you can use some of that data to validate your theoretical model and go on to say something more. But if you're proposing something new, it will be expected that you have some experiments to back up your claims, because it's often not easy to believe something if you just,
So I would take it from that you would be delighted to find some folks decide to go and work with you to build a prototype for your work, if you need some such people. Again, exactly, that's just a random thought on my part. I'm not suggesting that you do that. I think that is quite clear, and I thank you for taking time from your busy schedule of teaching and research to talk with us, and look forward to you being engaged over the years with us. And let's see what wonderful systems the engineering students come up with in this year's competition.
Thank you so much. I'm also looking forward.